Hi everybody, it's Mr. Zarzak, and in this video I'm going to talk about how we analyze 2D collisions using conservation of momentum and sometimes conservation of energy. Alright, so let's get started. When we talk about energy, specifically with collisions, what we really mean is conservation of kinetic energy. It's not that we can't have potential energy or spring potential energy or any of that kind of stuff. We're going to keep it as simple as we can and just talk about energy in terms of conservation of kinetic energy, and that's plenty. Okay, so when we set up conservation of energy, what's nice about it is we don't have to worry about any directionality, no vector stuff. All right, the only thing we have to be conscious of is this notation. When we see these little, so we're going to read this would be half mv squared plus half mv squared is equal to half mv squared prime. Okay, so that's what this is. This just means after. All right, we could apply the same notation to momentum. We see those little marks. That just means the momentum of the two before is equal to the momentum of both of the two after. So it's like p rho 1 plus rho 2 is equal to rho 1 prime plus rho 2 prime. Okay. We can always use conservation of momentum. That's the good news. The bad news, it's a vector, so we have to be conscious of that, the direction stuff, which means sines and cosines and all that fun stuff. All right, and then because of that velocity being a vector. All right. So taking all of that and just kind of simplifying it down to the bare bones, okay, momentum is always conserved. That's our first go-to. Unless, of course, we can do energy, all right? In order to apply conservation of kinetic energy, we need an elastic collision, all right? So we need some information that either tells us that energy is conserved or that's a perfectly elastic collision, or we got to be able to determine experimentally somehow in order to apply conservation of kinetic energy. Okay, but watch out, though, velocity is not a conservative quantity. We have conservation of momentum, conservation of energy. That's it. Okay, so anyways, let's try it. All right, so what I have here is I got a red ball and I got a blue ball, okay, and they're going to collide. All right, initially the blue ball is at rest. Okay, the red ball is moving at 4 meters per second to the side here. So it's going to hit the blue ball at some angle. As a result of this, okay, after the collision, we're going to force a 2D collision. See, so like the blue ball is going to go off in one direction, the red ball is going to go off in another direction. Okay, so our job is to figure out what's the blue ball going to do because we have this extra information here. The red ball, the 3 kilogram red ball after the collision goes off at 2 meters per second at an angle of 30 degrees, when before the collision it was just going straight to the left at 4 meters per second. Okay, so that's all given information stuff that I know. All right, the blue ball on the other hand, I know its mass. All right, I know it's initially at rest, but I don't know where it goes after the collision. I don't know which way and I don't know how fast. Okay, so that's what we're going to do is we got to figure that stuff out. The green arrows are momentum vectors. See, I have them marked here. All right, they're supposed to represent mass times velocity for each of the things, okay? Conservation says that the total momentum before must be equal to the total momentum afterwards. So if I take my momentum vectors, okay, so this would be like momentum of 1 before, and that accounts for all the momentum, see, because the blue ball is initially at rest. Okay, if I make another copy, this is after. So afterwards, the blue ball kind of goes like this, all right, and then excuse me, the red ball kind of goes like that, and the blue ball goes like this. Okay, so you almost kind of picture the collision in your mind. These two things, the one ball strikes the other ball, and then they split and go off in different directions. Conservation says before has got to be equal to after. All right, so if I take and I compare the before to the after, okay, so this is after, and so is this. Okay, my little prime got cut off. Sorry about that. Let me put the little mark on there. Rho 2 prime, rho 2 prime. Okay, anyways. So if I take these two vectors, the way that I add vectors is tip to tail. See, so like if I add it together, the momentum of 1 after and the momentum of 2 after, conservation says, is that those two things should add up to the momentum before. Okay, so really this is just a conceptual picture for conservation of momentum because momentum is a vector. Okay, I do have information about the red ball here. Okay, I know its velocity is 2 meters per second at an angle of 30 degrees. So since I have that information, that's what I'm going to use, all right? So the momentum and the velocity are going to be in the same direction. So I'm going to take and I'm going to draw another vector up here to represent the velocity. Now, if I was truly going to scale these arrows, okay, well, momentum is mass times velocity. So my scale factor for the momentum would be 3 for 3 kilograms. See, so this has a momentum of 3 times 2 is 6, all right? Technically, this angle should only, this red arrow should only be a third the length. I'm not going to scale these because then everything would be too small for us to actually see. Okay, so keep that in mind as these are not scaled, but this is a velocity vector that belongs to ball number 1. Okay, and it happens afterwards. All right, and I've got ball 1 and ball 2 labeled over here. Maybe I should put a label over here too. So this is also ball 1 after. Okay, and this is down here. This is ball 2 after, if that helps. Anyways. So I'm going to take this velocity vector, I'm going to break it into components. See, because the vector points up and to the left, so the components point up and to the left. So I'm going to draw those components, and just to make it clear that we are working in components. I'm going to make these little dashed lines just to make it kind of clear that I'm working in components. And then I have this angle. Okay, that's this little 30 degrees down here that I've got. So this is angle 1. Okay, the way that I would name these components, this would be V1 prime in the X direction, and this would be V1 prime in the Y direction. Okay, since I have information, I might as well calculate, or at least set up the calculations. All right, for the Y component, that Y component is right across or on the opposite side as the angle. That's my clue that in order to calculate, I'm going to use the sine function. So V1 prime sine of theta 1 is going to tell me what this V1 prime is. All right, now I have this 2 meters per second, okay, and the angle is 30 degrees, so I have enough information to calculate if I need to. So 2 meters per second times the sine of 30 degrees, okay, and I can put that in my calculator. I will at some point. I'll put it in my calculator when I actually need it, so for the time being, let's just focus instead on the X component. Okay, the X component is just the magnitude of the vector, so V1 prime. V1x is just right next to or adjacent to the angle, so this would be cosine, again, angle 1. All right, so then V1x prime is equal to 2 meters per second times the cosine of 30 degrees. Okay, and again, when I need to, I'll calculate it. I've got it set up now. That's good enough for now. If I look at the blue ball, okay, I don't know its speed, I don't know its direction, I don't know anything about its velocity, but I started this with the red ball's velocity, so we'll do the same kind of basic setup, all right, with the blue ball, at least in terms of drawing a picture, okay? So if I make this blue arrow represent the velocity of ball to after, okay, it's going to go off at some angle. I don't know what that is, all right? So the best that I can do is I can draw the components, all right? So V2 prime points down and to the left, so there's components that point down and to the left. And just like I did with ball number 1, the red one, okay, I'm going to take and make my components dashed lines just to make it clear that I am talking about the components here. I'll try to clean this up a little bit. I feel like that one's crooked. Okay, that's good enough. All right, and then this is my theta 2. I'm going to name all this, so this would be V2 x prime and V2 y prime. Now, I don't know the angle, and I don't know what V2 prime is either, so I'm not even going to write any equations. Like, if I need to write equations, if I need to do stuff with trig, I will. All right, but more often than not, all right, that's going to cause more work and more variables than I really want to deal with. I'll do it if I have to, okay? Anyways, so once I have all this, okay, this is my initial information. Now I can apply conservation of momentum. Now, if this was a one-dimensional collision, okay, first step would be to write the equation. So here we go. This is for conservation of momentum. M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, okay? In order to work within 2 dimensions, I literally have to do what I've always done is I look in the X direction, I look in the Y direction. So how does that change my equation? Well, masses are just scalars. They don't have a direction, but velocities do. So if I'm working within the X or the horizontal direction, okay, that means I have to work with the horizontal components of the velocity. See, so these all become little X's here, all right? And that's it. That's how I modify the equation to look at one dimension only. All right, so what else do we have here? The red ball is only moving initially to the left. All right, so I think since everything here is to the left, okay, and then up and down, there's no rightward stuff. So I'm going to make my positive direction to the right, okay? And also, the blue ball is initially at rest, okay? So then if there's no velocity, there's no momentum either, all right? So this simplifies down a bit. M1 V1x is equal to M1 V1x prime plus M2 V2x prime, okay? So then let's see, what do we have here? The mass of ball 1 is 3 kilograms. It's initially moving at 4 meters per second. So 3 kilograms, all right, 4 meters per second. And it's only moving sideways, so all that momentum is X momentum. Okay, afterwards, all right, we got 3 kilograms. Okay, V1 X prime. Do I have that? Well, I have the setup, so I can use it, so I will. All right, so at some point I'm going to have to calculate, so let's put it down here. Okay, so there's my V1 X prime. Okay, for ball number 2 here, I know the mass of ball 2 is 2 kilograms. Okay, but I do not know the horizontal or vertical component of its velocity. But if I do a quick scan here, lo and behold, I have everything other than this v2x prime here, which means I can solve for it. So I can get something. So let's do it. All right, so let's see. So 3 times 4 is 12. Okay, and then I have 3 times 2 is 6 times cosine of 30 degrees. Okay, plus 2 times this v2x prime. All right, so then 12 minus 6 cosine of 30 degrees is equal to 2v2x prime. And let's keep it blue so that we're tracking what we're solving for. Great. All right, so I'm going to divide over the 2 to isolate the variable. Okay, so 12 divided by 2 is 6. 6 divided by 2 is 3 cosine of 30 degrees. Okay, and that's going to be equal to my v2x prime. All right, so then that would be something I would want to go to my calculator in order to do. All right, so here, let's just go ahead and do it. So let's see, where's my calculator? All right, so 6 minus 3 cosine of 30 degrees gives me 3.402. 3.402 meters per second is equal to v2x prime. Okay, so I got something. I know the horizontal component of that sideways velocity. Great. What about the vertical part? Okay, in order to do that, conservation of momentum. Okay, so I'm going to cheat a little bit here, and then I'm going to steal this and just modify it. Okay, so a little bit of erasing here because we're going to work within the y direction now, or the vertical. That's a terrible looking y. Try that again. That's better. Okay, so then I'm going to, wherever I got these x's, I'm going to erase those and then just replace them with y's. Okay, so everything vertical. All right, good news. The blue ball still isn't moving to begin with. All right, so no moving inertia or momentum. Okay, so kind of like before, I get this setup where m1 v1y is equal to m1 v1y prime, which just means after, plus m2 v2y prime. Okay. Even more good news, the red ball is moving sideways. And how much of sideways is up or down? None of it. So ball 1 doesn't have any moving inertia to begin with in the y direction and the vertical direction either. Okay, it looks like I'm going to need a little bit more space here. Let me add in another page because that's the next problem. We're not ready for that yet. Okay, so then on the left side of our equation, we got 0. And then on the right side, we've got the after. How can we start with nothing before and get nothing after? Easy. All that means is that the momentum of 1 in the y direction afterwards is going to be equal to an opposite, the momentum of 2 in the y direction after. See? All right, ball number 1. Let's see. Ball number 1 was the 3 kilogram. Okay, so then I've got negative 3 kilograms, a little negative sign out in front. Okay, I don't know what that Vy1 prime is, but actually, yes, I do. Okay, or at least I know how to get it. Okay, so I'm going to do exactly that. I'll bring that down. Paste it in. I guess I didn't really need that extra parentheses there. Get out of there. All right, and then that's going to be equal to number 2. That's 2 kilogram. Okay, I don't know how fast it's going downwards, but now I can figure it out. All right. So then let's see. Oh, look, I can even factor out a 2. That's kind of nice. All right, so what am I left with? I got negative 3 times sine of 30 degrees is equal to v2y prime. Okay, and I just remember this, the sine of 30 degrees is equal to 0.5. All right, so just because I remember it, 3 times 0.5 or 3 times a half is 1.5 meters per second, and that's my v2y prime. Okay, and I got to keep my colors, so let's make all this blue and make this blue too. All right, now what does this tell me? It means that after the collision, ball 2 has a downward component, okay, with a speed of 1.5 meters per second. Okay, so if I have the horizontal component and I have the vertical component, I can solve for the overall velocity by finding the overall speed. Okay, so to do that, it's just good old Pythagorean theorem. So v2 prime is equal to the square root of v2x prime squared plus v2y prime squared. That quantity square rooted. Okay, so my v to x prime was this 3.402 squared, okay, plus this negative 1.5 meters per second squared. So v2 prime is equal to the square root of that. Okay, and I did calculate this one before, so I'm not going to. I'll spare you plugging the numbers into my calculator. You get 3.718 meters per second. That's the speed part, okay, of v2 prime. To get the direction, all right, if I go back to my picture here, okay, well, I now have v2y prime and v2x prime. So I've got the pieces. I've got the hypotenuse too, but I'm just going to use those originals so that I always tend to go to inverse tan, okay, of opposite over adjacent. So to get the direction part, okay, so direction 2 is the inverse tan of opposite. That's my v to y prime over adjacent. That's my v to x prime. All right, so there's my equation. It's been a little while, but we've seen this before. All right, so my x component is the y component. That's the one that's the negative 1.5. Oops. It just means 1.5 meters per second down. My x component is 3.402 meters per second sideways. Okay, if I take that and put that in my calculator, okay, my calculator is going to spit out a negative 23.794 degrees. Okay, so what that means, all right, is that, well, overall, okay, these two numbers here, okay, we have a speed of the blue ball after of 3.718 meters per second, okay, and the angle then is this 23.794 degrees below the horizontal. Okay, and if I just do one last little scroll back to my picture, okay, my theta is exactly what it's supposed to be. It's supposed to be some angle below the horizontal. I've got my speed, all right, which means that I now have all the information to say I know what the ball number 2 is going to do after the collision. It's going to go off with a speed of 3.718 meters per second at an angle of 23.794 degrees below the horizontal. These two numbers make its velocity. There we go. All right, now that's a lot of work. Okay, look at all this math that we had to do. All right, it's doable, but man, I wish there was an easier way. Okay, and the answer is that there is, if we're allowed to use energy. Okay, so similar kind of problem. All right, we got a 4 kilogram blue ball traveling at 3 meters per second, strikes a 4 kilogram orange ball at an angle. After the collision, the orange ball travels at 2 meters per second. If these balls have the same weight and energy is conserved, that's the key. Okay, if energy is conserved, how fast does the blue ball travel after the collision? Okay, so, so the blue ball comes in, hits the orange ball, goes off at some angle, the orange ball does too. Okay, great news. If its energy is conserved, no vectors, no thetas. Okay, we can figure out how fast it goes just by using conservation of energy. All right, specifically conservation of kinetic energy. So the kinetic energy of the blue ball plus the kinetic energy of the orange ball has got to be equal to the kinetic energy of the blue ball after plus the kinetic energy of the orange ball after. See, so like 1 and 2. All right, much easier. Look, 1/2 m 1v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, I can cancel out the 1/2s because they appear in every term, and they also say, oh, the same weight. Okay, well, remember, weight is mg, so if they have the same weight, they have the same mass too. So you know what? These m's are really all just the same m's. So they appear in every single term, which means I get to cancel those out too. Goodbye, 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 goodbye. All right, so then I'm left with v1 squared plus v2 squared is equal to v1 prime squared plus v2 prime squared. All right, even better news. All right, the orange ball is initially at rest. It's not moving. Okay, and so we have to use conservation of energy to get to this, but we get this really simple relationship. So we've got all the information we need to solve now. All right, the blue ball is going at 3 meters per second. v1 squared. Okay, after the collision, it says here the orange ball goes at 2 meters per second. So then how fast does the blue ball go? Okay, so orange here goes at 2 meters per second. So then how fast does ball 1 go after? All right, one equation, one unknown. We can solve this. So 3 squared, that's 9, is equal to v1 prime squared plus 2 squared is 4. Yeah, I can do this. Subtract the 4 from the 9. I get 5 is equal to v1 prime squared. And then just take the square root. So the speed of ball 1 after is the square root of 5, which I calculated that before too. So 2.236 meters per second. All right, this belongs to the blue ball after. Done. No components, no angles. All right, much, much faster if we can use energy. Could we solve this with momentum? Yeah, we probably could. Would I want to? Nah, I don't think so. All right. Well, anyways, so that's all I have for this video. That's more than enough. It just takes some practice. Okay, you can do it. So this is Mr. Zarzik saying thanks for watching, and I'll see you next time.